All right, everyone. Today we're going to be beginning our series on making a neural network from scratch with just a Jupyter notebook, some Python, and some NumPy. Our goal by the end of this series will be to solve a simple regression problem of fitting a curve to a parabola. We will construct a very simple neural network with 3 hidden layers, 1 input, and 1 output. For this series, I do assume that you understand the basics of forward and backward propagation, as well as basic object-oriented programming in Python. If you don't, I have linked some resources in the description that do a pretty good job at explaining them. In this video specifically, we'll be importing some of our dependencies, as well as generating and visualizing the data that we'll use in our throughout the series. In the next couple of videos, we will actually begin to code the architecture of the network, as well as things like forward and backward propagation. Okay, so let's get into it. The first thing we're going to need is to import NumPy as well as Matplotlib to visualize our data and our results. Now we can begin by generating our data. So we'll begin by making our input, which will be X, and we're going to use NumPy's linspace function. So np.linspace -3 to 3 comma 100. All this does is it creates a NumPy array with 100 equally spaced numbers from -3 to 3. Now let's go ahead and generate our output, which will be y equals x squared. So asterisk x asterisk 2. We can go ahead and visualize this parabola with plt.plot x, y. And as you can see, we get a pretty basic looking parabola. And our goal by the end of the series is to simply make a neural network that can, given some x value, return to us a value that's fairly close to x squared. Okay, that's just for this video. I hope you enjoyed, and I look forward to seeing you in the next part of this series. All right, hey everyone. This is our second video of the neural network series. Today we'll be making a layer class. So essentially, we're gonna make a object that's gonna allow us to handle all the values and parameters that our layers will need. So all the weights and the biases. Recall that the neural network we're trying to make is going to have 1 input, 3 hidden layers, and 1 output. Okay, so let's get started. We'll start by making a class and we'll call it layer. This layer class will have a couple attributes. We're going to need the attributes for the weights and the biases specifically. So we're going to input the number of neurons coming into the layer and the number of neurons that are going out of the layer. So essentially the number of input neurons and the number of output neurons. Okay, then we can go ahead and initialize our weight and bias attributes. Recall that the weight matrix is a matrix with dimensions neurons out by neurons in. The general ij term of this weight matrix corresponds to a weight that's coming out of the jth neuron in the previous layer and is going into the ith neuron of the next layer. So we're going to do this by using a normal distribution. So we have self.weights equals np.random.normal. We're going to use a distribution that's centered at 0, and our standard deviation will be the square root of 2 over the number of neurons coming out, so out neurons.
We use this just because empirically we find that it's the best value to use for our standard deviation. And then lastly, for our size of the matrix, as we just said, is going to be the number of neurons coming out of the matrix. So out neurons by the number of neurons that are going into the matrix. So in neurons. And then for the biases, this is going to be pretty straightforward. We will initialize the biases to zeros. So np dot zeros, and we're going to pass in the shape, which will be the vector or out neurons by 1. So it's a vertical column vector. The general ith term of this bias would represent the bias associated with the ith neuron. So this one's pretty straightforward, a little bit easier to visualize than the weights at least. All right, that's it for this video. In the next video, we will be going into making our actual architecture for the network. And after that, we'll discuss activation functions and forward propagations. I hope you guys enjoyed this video, and I look forward to seeing you in the next part of this series. Thank you. Hey everyone, welcome back to another video in our neural network series. In the last video, we made a layer class that would basically hold all our parameter values, all our weights and our biases. And in this video, we will dive into actually making our neural network architecture. We will essentially make a class that will help us handle this architecture, and the class will hold all the layer objects that contain the parameters. We will then need a constructor, and this constructor will have 2 arguments, namely input dim and output dim. So essentially, how many inputs does our neural network have and how many outputs does it have? And in our case, we have 1 input and 1 output. The next step is going to be to initialize our layers. We will have a total of 4 layers to initialize, 3 hidden layers, as well as our output layer. These layers will take the arguments of neurons in and neurons out as we structured it last time. And so the first layer, yes, will be input dimensions, comma, and I'll put 48, but you can put any arbitrary number of neurons. So feel free to play around with this number as you like. For the rest, I will put 48, comma 48 as well. So 48 neurons in and 48 neurons out. Except for the last layer, I'll make it 48 by output dimensions. Okay, so we have successfully coded a basic neural network. The next steps would be to code some activation functions as well as a method for forward propagation. And so look out for the video in a couple of days. If you want to play around with this architecture, go ahead and do so. You can change the number of neurons in each layer. I have it at 48 just because it's what I find works best for our current goal, but feel free to play around with that. And you can go ahead and test to see how this neural network actually looks like and works. So you can access each of the layer objects and see all the weight values as well as all the bias values. All right, that's it for this video. I will see you in the next one. Thank you. Hello, everyone. Welcome back to another video in the neural network series. Today, we'll be programming a method to handle the forward propagation aspect of our neural network as well as our activation functions. Forward propagation is really the main way that our neural network processes information. When you give a neural network certain inputs, these inputs are then passed in through the network's layers where basic operations are performed on them. These operations are all handled with matrices and obviously our activation functions. If you'd like to know more about the math behind these operations, I have linked a good resource in the description. Okay, so let's jump into the code now. We'll begin by writing one useful function in our layer class, which will allow us to call our layers as functions. This is the built-in call method in the Python, and we write it as such, surrounded by double underscores. The function will take in self and a vector of inputs, which we will call x. Then we will simply return our weight matrix, self.weights, multiplied by this vector x, and then add it to the bias vectors, self.biases. All right, cool. Now let's move on to the activation functions, and then we'll be ready to make a forward propagation method. There are many different ways you can choose to organize your activation functions. Generally, it is a good idea to make a class that will hold all your activation functions in the same place. In this series, I'll mainly be utilizing the ReLU activation function, which is the rectified linear unit, but I encourage you to try using different activation functions if you'd like, such as the sigmoid or hyperbolic tangent functions. The ReLU is a pretty popular choice, mostly because it's a pretty straightforward piecewise function that returns the value passed into it as long as it is positive. Otherwise, if it's a negative value, it will just return 0. We will achieve this behavior with the NumPy vectorized maximum function that basically just returns the max of whatever two inputs you put in it. So in this case, 0 and z. I'm using z here just because it's common notation for the pre-activated values. All right, so we will modify this class a little bit more in the next video, but for now, we're good to move on to the forward propagation function. In my network class, I will call this function forward, and it will take in arguments self and x, which will be a row vector. Next, I will initialize an activation object, which will allow us to call the ReLU function we just made. Then our first input, which is x, is going to be passed into our first layer. And I'm going to call this self.z1. And because of the call method we just wrote, we can call our first layer using the function notation, which is really nice. Then we can go ahead and activate this value. So self.a1 for activated value, and we're going to do f.ReLU to call the ReLU activation function we just made. And in parentheses, I'll put self.z1. Cool. Now we literally just repeat this for all the layers. So for the second layer, I will do self.z2, and we will then pass in the activated values of the previous layer into the next layer. So self.l2 and in parentheses self.a1. And then again, I will activate these with self.a2 equals f.ReLU self.z2. Nice. So with that, we have a forward propagation method. As you can see, for the final output, I called it self.output instead of self.z or a. And also, I did not use the activation function for the output value, but you can feel free to try that and see what happens. It's usually uh, not conventional. Okay, now we can go ahead and test this. Before we do that, as a quick disclaimer, the way we have coded this is that all inputs x are going to be a row vector. This will make passing in values in bulk down the line a lot easier. But just be careful if you're trying to plug things in and they're giving you a dimension mismatch error. Okay, so I'm going to go ahead and pass in x values. These are x values we created in the very first video of the series, and I'm also going to reshape them as a row vector because of the reason I just stated. And if we go ahead and plot this, you can see we get a pretty abysmal output. And that's mostly because this neural network is untrained and the weights and the biases are kind of just random. So in the next video, we will go ahead and actually code a backpropagation algorithm, which will allow us to adjust the weights and the biases to make a trained neural network. And this neural network will then actually be able to fit to the parabola, which was the original goal of this entire series. That was all for today, and I'll see you next time. Hello, everyone. Welcome back to another video in the neural network series. Today, we'll be programming a backpropagation method for our neural network. Last time, we made a forward propagation function, which is really the main way that a neural network processes information and returns the outputs that it does. However, if you remember from our video, the outputs that we got were pretty meaningless, and that was because the network hadn't been trained yet. And so backpropagation is really the key algorithm responsible for allowing the neural network to train itself. The basic idea behind the backpropagation algorithm is that we're going to take the output that we get from our network and compare it to the desired output and then calculate some sort of loss metric on it. And then this loss is then propagated backwards through the network. And we then calculate the amount by which we want to change each of our parameters, namely the weights and the biases, to most effectively decrease our loss. This is a very, very famous algorithm, and most of the math behind it is um, chain rule and just some basic matrix multiplication. So if you'd like a more detailed video on the math behind backpropagation, I've linked a video in the description that I think does a pretty good job. Okay, let's dive into the code now. I will begin by making a function that is basically the derivative of our ReLU activation function. We need this derivative as it ends up popping up when we do our chain rule in backpropagation. The method itself is pretty straightforward to code. If our input is positive, then our derivative is 1. Otherwise, the derivative is 0. And this is due to the fact that the ReLU function is a piecewise function. Cool. Um, we're going to use a sort of a neat trick to implement the piecewise nature of this function. Instead of using an if-else statement, we're going to use the NumPy where functionality, which essentially is an if-else function, except it's vectorized, so it mitigates the use of a for loop. Cool. Now we can begin our backpropagation function in our network class. One quick change that I did make from the last video was that I made the activation class object f a class attribute. So now we can access it throughout the class without having to redefine it every single time. Note that, however, now you do have to call it with a self in front of it, so in self.f instead of just f. Okay, so let's start by filling in the arguments that this function will take in. We will need to pass in self, obviously, and also x, which is going to be the input, and y true, which is going to be the desired output. Cool. Now, the first thing we're going to need is the derivative with respect to the cost function. The cost function we're going to use in our case is the toNorm, which is essentially the squared, the sum of the squared difference between the desired value and our predicted value. And the derivative of this function is pretty straightforward. It's simply going to be 2 times the predicted output minus the desired output. Next, we will go ahead and find out the error terms. You can do this iteratively using a for loop, or personally, since we just have 4 layers, I'm going to be hard coding them in. But as the number of layers in your neural network increases, it might be a good idea to switch to using a for loop. Okay, so we begin by finding the error term of our last layer, so del 4. This happens to be the same as the derivative of our loss. So del 4 is just going to be equal to dc. Next, we'll find the error term of the third layer. Here we will need to take the derivative of our pre-activation values with respect to our activation function. And we're going to do this for the pre-activation values in the third layer. And so we call self.f.drelu on self.z3. Then this gets multiplied element-wise by the weights in the fourth layer, specifically the transpose of the weights. And so we will call self.l4 for layer 4, dot weights, and dot t for transpose. And we use the asterisk here for element-wise multiplication. Cool. Then this will get matrix multiplied by the last layer error term. So in this case, del 4. And we will use the at symbol for matrix multiplication. Now we just repeat this process for the other two layers. So going to the del 2 term, we will do the same thing. We will have the derivative of the pre-activation values in the second layer, self.f.d self.z2, and then this would be element-wise multiplied by the weights in our third layer, so self.l4.weights.t for transpose. And then lastly, that gets matrix multiplied by the error term of our last layer, so at del 3. Cool. So now we have found all our error terms, and we need to now find the gradients of all our parameters. These gradients will essentially tell us how much each parameter needs to be perturbed to decrease the error in our outputs. For each of the weights, all we need to do is matrix multiply the error term with the transpose of the activation values of the previous layer. And that will be del 4 at self.a3.transpose, or .t for transpose. We will do the same for the weights in the third layer. And so del 3 at self.a2.t. And then same thing for the second layer, del 2 at self.a1.t. Cool. For the first layer, we will not be multiplying by the activation values. Instead, we'll simply be matrix multiplying del 1 with x, our input value, specifically the transpose of x. Lastly, for the biases, the gradients are pretty simple. These are just our error terms themselves. So self.db4 is del 4, self.db3 is del 3, and so on and so forth. Cool. And so with that, we have found all our gradients using backpropagation. And in the next video, we'll be implementing the gradient descent function that uses these gradients to actually change the parameter values themselves and actually train the network. Cool. I hope you all enjoyed this video, and I'll see you in the next one. Hello, everyone. Welcome back to another video in the neural network series. Today, we'll be making a gradient descent method that will finally allow us to train our neural network. So gradient descent is used in a lot of optimization problems, and at its core, training a neural network is just an optimization problem. And we're really just trying to get our network's output values to be as close as possible to our desired values. If you remember in the last video, we used backpropagation to find the gradients with respect to the parameter values. Now we will use those gradients to change these parameter values in such a way to maximally decrease our error. Okay, let's jump into the code now. We will be making this method in our network class, and the arguments taken in by this method will be self, as always, and learn rate. The learning rate will help us change the speed at which our neural network trains at. So a smaller learning rate will result in smaller steps taken by the network each time, which would lead to more granular and detailed learning. However, larger steps will allow you to converge to some optimal value for your parameters a lot faster. Note that smaller learning rates aren't always better for best results, because you can get your network to overfit sometimes. However, it really depends on the problem, and it's all going to come down to experimenting with different learning rates to figure out which one's the best for your problem. This is a very famous part of neural networks and just machine learning in general, known as hyperparameter tuning. All right, now let's get into actually writing the body of the code. So all we need to do to update these parameters is subtract the learning rate times the gradient of that parameter. So we will do self.l4.weights minus learn rate times self.dw4, which are the gradients of the weights in the fourth layer. And we pretty much do this for the rest of the parameters, including the biases. And let me just quickly speed through this. All right, and this is our final product. With that, we have successfully made a gradient descent function that helps us train the network. Now we're left with one final step, which is to make a training loop. And this will be outside of the network class. So I encourage you to try and code the training loop yourself. It's not very difficult, so go ahead and give it a shot. But I will upload a video soon detailing the code for the training loop and testing our network to actually fit to the parabola, which was our original goal, as well as some hyperparameter tuning. All right, this is all for today. I hope you enjoyed the video, and I will see you next time. Thank you. Hello, everyone. Welcome back to another video in the neural network series. Today, we'll be adding the final piece to our neural network by making our training loop. We have all the tools that we need to get a network that trains itself. All we need to do is put them in the correct order. The basic idea behind our training loop will be that we will essentially let our network train for a couple thousand iterations, and then in each iteration the network will change its parameter values based on the desired output and the network's predicted output, which obviously uses backpropagation and gradient descent. Alright, let's jump into the code then. And we're just going to go ahead and call this method train. And this train method will take our network, which I will call model. It will take X, which will be our inputs, and it will take Y, which will be our desired outputs. And then the last two hyperparameters it will need will be our learning rate, which is used by the gradient descent method, and then the number of epochs, and I will set a default value for this of 10,000. Okay, let's move on to the body of the code. We will have a for loop, so it'll be for epoch in range epochs, colon. So pretty straightforward. Next, we want to be doing something that's called stochastic gradient descent, which is really just a fancy way of saying that our inputs that will be used to train the network in each iteration will essentially be random. And so in order to get a random input at each epoch, we will do index equals, and we'll utilize the NumPy random functionality, so np.random.randint, rand_int essentially produces a random integer, and we want our range to be from 0 to the size of our inputs. So x dot size, and this upper limit is exclusive, so it doesn't include the final number. Okay, we can then go ahead and get our random input. So x equals capital X bracket index, and so this index was randomly generated, and now I'm just accessing the value at that randomly generated index. And then I'm going to go ahead and reshape this input as a 1 by 1 matrix, essentially. And then the next thing is we can go ahead and get our desired output value, so y underscore true, and this would be just y bracket index. Cool, now we can actually train our method. So the first thing we're going to need from our network itself is the predicted output value. So I'm going to do y underscore pred equals model, which is our network, and we're going to go ahead and call the forward method, and then this essentially calculates the predicted output and stores it in the class attribute. So now we have to essentially use this predicted output from the network to calculate all our gradients. And if you recall, we do that with our backpropagation method. So next we will call model.backward, and we will be passing in x comma y true. Lastly, we need to use all these gradients to actually change our parameter values. So for that, we'll be using the gradient descent method. So model.gradient descent, and we'll be passing in our learning rate. So learn underscore rate. We can add a print statement just so we can actually track the progress of our network. Okay, with that we are officially done. Now we can go ahead and train our network and see if it actually works, if it actually fits to the parabola that we initially had. So let's first go ahead and make our network. So we will do model equals network, and then I'll pass in 1 comma 1 since we have one input and one output. And now we can train the network using the train method. So train, pass in our model, our inputs x, our outputs y, our learning rate, which I'll set at 0.001, and the epochs, which I'll just keep at 10,000. If we go ahead and hit enter, shift enter, you can see that our network starts to train, and over time our losses are decreasing, which is a good sign. It goes up a couple times, but the overall trend is that the losses are decreasing, which is what we want. Okay, now we can actually visualize the results by plotting the predicted values versus the actual values. So to get all our predicted values at once, we'll do y underscore pred equals model.forward, and then we'll have x.reshape 1 comma 100. So I'm just reshaping our inputs to a row vector because that's the required vector by our for method. And then we can go ahead and plot our values. So I would do x comma y pred, and then I'm gonna go ahead and put a bracket 0 in there just so it actually quote unquote flattens the list. It just doesn't have a matrix in there. Otherwise you'll actually get an error. And then shift enter, and boom, we have something that's pretty close to a parabola. And so you can see that we have officially actually trained our method, and the outputs this time are not completely meaningless. With that is all for today's video. We have now finished our neural network series, and I do plan on coming back to this series sometime, and making our neural networks tackle some more complex problems like classifying images and other categorical data sets. Let me know in the comment section what else you would like to see, just in general, or just related to neural networks. I think maybe implementing some sort of a atom optimizer might also be a good idea. And that's all. So thank you, and I'll see you next time.